One. Hello everyone, welcome back to our YouTube channel, Becoming a ROS Developer here at The Construct. My name is Rodrigo, and today we have one of our students who has completed the course ROS Basics in 5 days, and this is in Python. And at the end of this course, you can present a project with us to get a certificate in which you actually implement your programs on a real robot. So that's what we're going to be seeing here today. That's it for us. So hello, Ben, how are you?
I'm doing great. How are you doing?
I'm doing great as well. Very excited to see your project. So whenever you want, you can start sharing your screen and just explain us how you've achieved what the project is.
Sure. The uh, project is still loading up, so I can go into my slides that I've created here.
Perfect.
Hold on, let me get this out of the way. There we go. Alrighty. All right, so a little bit about me. My name's Ben. I'm a Master of Science in Aerospace Engineering student at the University of Houston, and my study focuses in control systems. Kind of some of the contents I'm going to be talking about today. I structured this in the order of which the code is ran for the project. So first I'm going to talk about my wall finder script, then I'll go into the odometry recorder, and then the following final launch file that spins all the nodes, and then some of the things that I ran into and some of the things that I learned from those complications. So first, the wall finder script. I subscribe to the scan topic, and I create a publisher for the command velocity topic. I'm using callbacks for the laser scan and the find wall service request. And then I use a multi-threaded executor for scan and command velocity using 2 threads. The logic I use for the wall finder code, I'm capturing the shortest ray distance right when the code starts, and I set that as the wall. I rotate the robot until the absolute value of the shortest ray minus the front ray is less than a tolerance value that I can give. So as it's moving, that value gets smaller and smaller as they become sort of the same value, and then it knows, okay, I'm in the right spot. The robot then moves forward until that front ray minus the desired value from the wall, which is 0.3 meters, is the same value. Then it stops. And then I rotate the robot until the right ray index minus the shortest ray index is the same value as well. Then once it's complete, it sets a response that the wall has been found, and then the wall following code starts. So then for the ODOM recorder script, I'm setting up an action server named record ODOM. Using the ODOM record action type, I subscribe to the ODOM topic to receive the odometry data, and then I take advantage of multi-threaded as well in this script as well. The logic I'm using for the recorder, upon receiving the goal to start odometry, the action callback function waits for the start point to be identified, and then it begins executing. It records the odometry data, calculates the distances, and updates the total distance traveled every second. So I have it updating every second. It's giving me feedback. And then I have a lab checked completion. So once the robot gets within a certain distance of its start point, it knows it's done, and then it'll spit out the points that it's logged and its total distance. And finally, for the wall following script, it kind of brings everything together. So I'm setting up clients for find wall, ODOM record. It waits for those to become available, and then it begins. So I have loops running at the start of the code to make sure those are good. First, wall finder. It won't continue until the wall is found. So wall finder finishes first, then wall following can start. And the logic I use for wall following, um, it's nested if statements. So it's checking first the distance of the right ray index. If it's too close to the wall, it moves in the negative z direction. If it gets too far away, it moves in the positive z direction. And then I have a parallel check with the positive 5-degree ray index of the right ray and the minus 5-degree index of the right ray. If I'm checking the distance of those two rays, I can actually show it here a little bit better. I'm checking the distance of those two rays. If one is further than the other, it adjusts its z orientation so that those distances match up, but I have it within a tolerance value as well because they'll never be exactly the same. So yeah, and then I have kind of showing here the ray values changing from the sim to the real, known as the sim to real gap. And yeah, and then the launch file that launches all of these nodes. Yeah, spinning all the nodes at the same time. And then some of the complications I ran into during this project, determining the correct laser index information from the simulation to the real robot. Using ROS 2-topic echo / scan, I was able to determine with the min ray value and the angle and the max angle, and then the increments of the rays. And I also set up a test function that had live loggers where I could use a telop keyboard, move the robot around. So if I had an idea of what I thought the right ray index was, I could test it with this code to see if my idea was correct or not. Also, the publishing speed on the simulation to the real robot was very high. So using the echo command velocity function, I had to set up sleep timers in the wall finder code because what was happening in the real robot, I would finish the wall finder code, like the robot would be done, it would find wall, but it would still continue to maybe move a little bit too far, and it would be like off kilter a little bit. So and then I then found out that it was receiving too much information, so it wasn't stopping at the correct time. So I had to implement sleep timers in the wall finder to make it work correctly. And then also getting all 3 nodes working in tandem at the launching the main launch function. So setting up while loop flags was another thing to work on, so that everything worked in the correct order. So wall finder would finish, and then odometry and wall following would start at the same time as well. So
All right.
now let's run it.
So you said that the wall follower was a nested if statement, right? That's
Correct.
and the two is checking the right side and then also the +5 and -5 degrees.
Correct.
And is that some sort of that's an if and else, or is that like a PID controller or something like that?
It's an if else, and I will say that it's not the best. Once I run it, you'll see.
Okay.
I think it could have been improved, but I got it to work, so I didn't really mess with it too much. It does work, but it definitely could be improved.
All right. No, I mean, if it does the job, it does the job. So
yes.
let's look at it. Yeah. So that's a good practice that you're compiling. But if you actually didn't change anything and it should like the build and install should stay the same, so you wouldn't need to compile at this point.
Oh, I actually didn't even know that. Okay, ROS to launch. Um, what was it? Wall. Right. So right off the bat, you'll see I have loggers showing the distance difference for
Mm.
this first initial movement as it's rotating to find the wall. And once this value gets within a tolerance threshold that I've set, it'll then move forward. And then now it's rotating so that the right side is lined up with the wall.
Yeah, yeah.
Now it's finished, and now the wall following starts. And then this is when it's starting to um, show the odometry data every second. I have it updating. Can maybe make this a little bit bigger so they
Yeah, yeah. And
fit a little
that's the
better.
total distance. That's the action, right? That's
Yes,
the
it
leg.
is.
Yeah.
Yeah, so I have this current total distance, and then I have this distance to goal. So this is also that set value. Once it's within, I have it set to 0.05 meters. Let me make sure that's correct.
Yeah, I think that was the instruction. It doesn't really matter
Yes,
though.
within 0.05 meters. Then it should know that the lap is done, stop, and then output the total distance traveled. So
Uh-huh.
yeah, as you can see, it kind of gets off kilter, then it lines back up, and so it's not following the wall very precisely, but
It's catching it. So,
um,
all right.
yeah,
And
yeah.
and now
And then now,
I think it might miss it because it's a
yeah,
quite small.
yeah, I think it
Um,
did miss it,
yeah,
unfortunately.
don't worry, because this is a non-important, but that's because the movement is kind of
It's
making it hard for that 0.05
yes,
to be achieved. But
yes,
so first of all, really nice job, Ben. Really nice, really clear, and clear example. So let me just do a couple of comments. Uh,
sure.
so the reason why I was asking about that +5 -5 because that's a really really good idea. So I really like that you thought of that, and it actually can take care of. I think so. If you maybe not like 5 and 5, maybe you have to extend it a little bit for when there's a hard corner, But
Mm,
you could actually um, create, like, get rid of the looking at the right and the front, if else, to do that movement,
mm-hmm,
and just look at the error between, like, the difference between those values, right? So you were
mm-hmm,
saying, like a little bit above the right side, a little bit below, and you can actually do what I said about a PD. I don't think you even need a PID. You don't need. It's just a potential derivative,
mm-hmm,
and you can look. I found it on. I look it up online every time I need a simple one. It's just like it's like a simple class, like a controller class on Python, and
mm-hmm,
you input the error you want, which would be basically your +5 distance minus your -5 distance should be 0 all the time. So
mm-hmm,
every time the node spins, it's checking for that distance. So it would automatically sort of, you know, stay on top, stay parallel to the wall. And again, it
mm,
might be a little bit complicated once you get to that corner because of how close you'd be to the wall or how
mm-hmm,
fast you'd be going. It would be a matter of tuning. But that's a really good idea you had, and it's actually how a lot of things work in real life. For example, I have a robot that I need to make it go charge every couple of hours, and the way I do it is exactly that way. I just run a PD controller so it localizes itself. I needed to move around so it finds itself because
mm-hmm,
I'm not able to tell it where it is, and basically it just starts going along the wall. And once it hits a corner, that difference becomes greater, and it just adjusts. So that I would follow down that line in order to sort of smooth out the movement because that would be just a couple of line changes. And I just wanted to mention because that's a really good idea. And it actually, I mean, it's really useful for a ton of applications.
Yeah,
But
that's a great point. I think right now what the code is doing is it's going through each one and then
uh-huh.
it gets to the parallel check and then it's trying to adjust back with what's above it and then
Right.
so I think what you're saying is correct, maybe focus on just having one of those checks and
Mm-hmm.
then it would be a lot smoother.
Yeah, so the only variable then you would choose that you would input in that, like the controller output, is just the angular velocity. So
Mm.
the distance is too different. You know, it's a
Mhm.
lot bigger than zero or the absolute value of zero. So
Mhm.
it would just adjust really hard or really softly depending on what it is. But um, but yeah, I mean that's a really really nice project, Ben. So congratulations. So a little applause for you here, and
Thank you.
really really nicely done, really clear, and yeah, I mean we see it still going.
I know
The
it still hasn't gotten to that threshold.
which means it's probably never gonna do it now because
Yeah.
the odometry keeps increasing. But that's just a still little detail that I think I should change. I should set 20.2 instead of 0.05, and then no one will have that issue because it's not the
Right.
point of the project. The point is to achieve this motion we're seeing on the screen with the three main basic things from the course. So I just want to congratulate you, Ben, and a really nice job.
Awesome. Thank you so much.
All right, let me just go back here to my screen, and yeah, uh, guys, this is what you can do when you take our courses. You can come and present what you've learned in order to get a certificate and just showcase what you've taken out of our courses on a real robot. So I encourage everyone to do what Ben did here and showcase what you've done with our course. And yeah, thank you one more time, Ben, and I hope to see you again very very soon.
Awesome. Thank you.
All right, guys. That's it for us, guys. We'll see you at the next presentations. All right. Bye bye. All right.